Hello, my name is Bill Kinney, and this is the third video on my series on large and small numbers, scientific notation, accuracy, and precision. I'm going to go over the two examples I went over in the first couple videos. This one is about U.S. population being 313 million people. How precise is it? How accurate? Write in scientific notation and put it in perspective. First comment I want to make is that this calculation down here can also be done with scientific notation. 500,000 is the same as 5 times 10 to the 5th power. 313 million is the same as 3.13 times 10 to the 8th power. What you can do is you can think of this as 5 divided by 3.13 times 10 to the 5th divided by 10 to the 8th. And 10 to the 5th divided by 10 to the 8th can be written as 10 to the 5 minus 8. You can subtract those exponents there. If you do the calculation, 5 divided by 3.13, you get about 1.6. So this is about 1.6 times 10 to the negative 3rd power. There we have 0.0016 in scientific notation. You can get from here to here by realizing you'd have to move the decimal place 0.3 places to the right to get it just to the right of the first non-zero digit, like that. And you can go from here to here by taking the decimal here and moving it to the left 3 spots to get that. I've written this number with 2 significant digits in both spots. It's got 2 significant digits. It's easiest to see perhaps here, but it is true here. These zeros are not significant. If they come after the decimal like that, you only count the non-zero digits there to be significant. Though if I did put a 0 after this, if I put 0.00160, then that 0 that comes after would be counted as significant. I'd like to also put this number in perspective, the 313 million people. I did it before by estimating how long it would take it to shake everybody's hand and got about 50 years of non-stop handshaking. We could also put it in perspective by imagining if we lined up head-to-head women, say, around the Earth, how many times would they go around the Earth if you had 313 million of them? Although, imagine every person in the U.S. being a woman, and if you line them up around the equator, say, how many times would they go around the Earth? That's another thing you can imagine. You'd have to make some estimates. You might say the average woman is about 5.5 feet tall. And let's, just for the sake of doing it, to show we can, let's convert that to meters. It turns out that there's 3.28 feet per meter. So if I take 5.5 and divide it by 3.8, which you can 3.28, excuse me, which you can try on your calculator, you'll see you get about 1.7 meters. Let's just pretend, for the sake of argument, that that's the average height of a woman in the country. Now we all line them up. We need to know the circumference of the Earth. The Earth's circumference turns out, I looked it up, is about 40,000 kilometers. We could either convert the height to kilometers or we can convert the circumference to meters to help compare these. It probably would be easiest to convert that to meters. Multiply it by 1,000 since there's 1,000 meters in a kilometer, so I need to add 3 zeros to it. 1, 2, 3. That's 40 million meters around the Earth. And so how many women are of height, average height 1.7 meters are going to fit around the Earth if you put them head to head? We'd have to just take 40 million and divide by 1.7. And we get, if you look at that, that's 23,529,412. That's got too many significant digits. Technically, since this number is, the implied precision is to 1 significant digit to the nearest 10,000 kilometers, I think it's, let me just pretend it's accurate to the nearest 2, to the nearest 1,000 kilometers. when I write it this way, the implied precision would be to the nearest 10,000, but you could verbally say this is accurate to the nearest 1,000, so that I could say this first zero here is significant. Let's just pretend it is. Then I'd want to round this to the nearest million women, and that would be 24 million women of average height 1.7 meters would go around the Earth. 313 million divided by that number, which I'm gonna use all the digits there, essentially says it's gonna, all these women from, if every person in the US was a woman of average height 1.7 meters, and you line them up head to head around the Earth, they're gonna go around the Earth about 13 times. That's what this says, the fact that I took the 313 million and divided by this. Don't use the rounded form of it, use the more unrounded form. Only round at the end, keep more accuracy, more precision, excuse me, as you go, and only round things at the end. The answer would be to go around the Earth 13 times. We could do a similar perspective thing with the virus. Typical virus was a diameter of 100 nanometers. That turns out to be 100 times 10 to the negative 9th meters, or in ordinary scientific notation, 1 times 10 to the negative 7th meters. How could you put this number in perspective? We could imagine what would happen if I blew up the size of a virus to being 1 meter in length, and then line them up around the equator. How many times would they go around the Earth if they were all 1 meter in length? Well, an actual virus, again, is 1/10,000,000th of a meter. If I then imagine scaling those up to being 1 meter in diameter, and imagine, okay, the original viruses lined up, you'd have 10 million of them would be in a meter. If this is 1 meter in length, you'd have 10 million viruses. Now imagine scaling this up so that those 10,000 viruses were all lined up, but they're all 1 meter in diameter. How many times would they go around the Earth? Well, again, the circumference of the Earth is 40 million meters. That's what I wrote in the previous sheet. So they're actually not going to go quite around the Earth. They're going to go about a quarter of the way around the Earth if each virus is 1 meter in diameter, and you line up 10 million of them, then they're going to be lined up over 10 million meters. And again, the circumference of the Earth all the way around the Earth is 40 million meters. So this would go a quarter of the way around the Earth, which is still pretty significant. I'm in Minnesota. If I imagine going down to the equator, south of here, and going a quarter of the way around the Earth, probably I would be in Africa. So line up those viruses 1 meter at a time. 10 million of them would reach to Africa. And that's a way to put that number in perspective. So there's lots of ways to put numbers in perspective, and I'm just illustrating some of them. I guess I have another minute or so here. Maybe it'd be good to also emphasize what's going on here. How would you, this number is the standard form for scientific notation with this. How would you put that in regular notation? Might be a good thing to end with here. Well, the decimal is assumed to be right after the 1 there, even though I haven't written it. So if you imagine it being right after the 1 there, to write it with regular notation without scientific notation, because that power is -7, I have to move the decimal 7 spots to the left. And if you think about that, that means there's going to be 6 zeros to the left of the 1, but to the right of the decimal. That's going to be how many meters a typical virus might be, and that is 1/10,000,000th. That's the 10th spot, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionth spot. That's 1/10,000,000th of a meter, and that'll be what I close this video with.